Welcome to MECH 2020 Statics and Dynamics Tutorial 2. Today the tutorial topics are 3D forces, complex vector operations, and moment. In this tutorial, we will cover vector forms in 3D space, dot and cross products, and the magnitude and axis of moment. So last tutorial, everything was covered in 2D for simplicity of concepts. Now we will cover 3D vectors and forces to prepare you for moment calculations. The rectangular form of the 3D vector is very similar to the rectangular form of the 2D vector, just that another axis has been added. The vector notation now adds a k component in the positive z-axis direction, and the absolute magnitude includes a squared z component inside the Pythagorean square root. Here we introduce the concept of unit vectors. This unit vector is a vector of magnitude 1 unit. So let's draw this here. And its components can describe the directions of much larger vectors than it. It just needs to be multiplied by a scalar non-vector magnitude to match the magnitude it wants to describe. The unit vector of a vector AB can be found by dividing the components of the vector AB with the magnitude of AB. So this here is actually magnitude AB. In this course, we will describe a unit vector with the Greek letter lambda. This will be used in dealing with more complex 3D polar forms. Now, we'll discuss some comparable forms between making a polar vector form of a 3D vector and its rectangular form. Obviously, making and defining a polar vector form in 3D is more complex than adding another axis of measurement. In 2D polar form, we have a magnitude, an angle, and a reference line in order to create the polar form. To make a direct comparison with 3D rectangular form, we can use the XYZ coordinate system as reference lines and have the angles between the vector and each axis, as well as applying the magnitude to the vector. This polar vector form is the description by direction cosines. We have a graphic here detailing how the angles would be taken. In the direction cosines method, you take the angle between the free space vector, this vector here, and any of the axes of measurements, and find the angle between them. So say we wanted to find theta z. So this is theta z here. This angle is then called the directional angle of that axis. Its cosine value, or cosine theta z, a little better, multiplied with the vector magnitude. So vector magnitude, the vector magnitude here is f, is the value of the vector component in that axial direction. So this is equal to fz. For most 3D problems, sticking with the rectangular form is much simpler for calculation, so you don't have to deal with these sorts of angles. Force equilibrium is calculated in the same way that it was in 2D, except with the addition of a z-axis equilibrium equation when calculating the summation of forces. Now, let's do a 3D resultant force problem. Please pause the video and take 5 minutes to attempt this problem yourself. Now that you have attempted this problem yourself, we'll go over our approach. First, we deconstruct the problem into a free body diagram. We know the absolute magnitude of tension in cable AB, the cable rectangular components of all 3 cables, and we need to find the weight of the object, which is a point straight downward. So we'll take note here, they're all attached to the wall, which means that they have the same y vertical height. The only difference is in x and z coordinates. From this information, we can find the trigonometric ratios of each cable's tension and break each cable's tension into rectangular components. Since the system is in equilibrium, the net forces in all directions should be equal to 0. We use the dimensions here to generate unit vectors and to help directly solve the force magnitude variables. From this, we use vector addition to form a system of equations to find the unknown values in AD, AC, and W. Here is the full breakdown of the system of equations. Note that all the variables in the top equation have a right-pointing arrow above them. This indicates that the variable is a full vector and not just a component of scalar value. From our system of equations, we can solve all values indicated with the substitution of givens, starting with the Fx equilibrium equation. Thus, we have found the weight and solved the problem. Now we'll cover some more vector multiplication types. Earlier we mentioned scalar multiplication, which is a magnitude multiplied onto a base vector, but there are more important types to cover. The first thing that we will cover, and have already been using to an extent, is dot product multiplication. The dot product multiplication of two vectors produces a scalar quantity that is equal to the product of their magnitudes and the cosine of the angle between them. Dot product multiplication follows the commutative and associative property of multiplication. The dot product is a very versatile tool in our arsenal with many applications. The dot product can solve an angle between two vectors by finding the angle's cosine. The other equation for a dot product is that of manipulating the rectangular vector forms of the vectors, as shown in this slide for the dot product of vectors A and B. So, this equation. The dot product can also be used to find the projection of a vector onto another vector by dividing one of the vector magnitudes. This we have already been using to convert vectors into rectangular form. If we recall that sine 90 minus x is cosine x, we can see that conversion from polar form to rectangular form is all dot product operations. Next, we will cover the cross product, which is a unique vector multiplication operation. A cross product on two vectors generates a final vector that is perpendicular to both vectors in space. It does not follow the commutative property, as reversing operation order gives a negative version of the initial output vector, but does follow the associative property. The absolute magnitude of this vector is equal to the product of the magnitudes multiplied with the sine of the angle between the two initial vectors, as seen here. To calculate a cross product operation, we use a construct known as the determinant to organize the vector information. The usage of the determinant is detailed in the slide here. In the diagram shown, the center of the T formed is the corresponding axis values for which we are calculating for this smaller square form. So for this one it would be I, for this one it would be J, and for this one it would be K. So we can split this into smaller vector, or the smaller determinants here, where we have 1, 1, 3, minus 2, I, plus 3, 1, minus 1, minus 2, negative j. Let's note that that's a negative j over there. That's just the rule that we follow for 3 by 3 determinants. If you're taking linear algebra, later on you'll learn that this is a part of cofactor expansion. Plus 3, 1, negative 1, 3 in the k direction. Alright, so we've broken it down into these smaller determinants here. So what do we do now? We look at the order, we can see the order of operations using the arrows here. So the arrow 1, so 1 is to be multiplied with -2, and the 1 here is to be multiplied with +3. And this is to form the calculation shown here for cross products in general, or for 3x3 cross products. So there we have our final answer here, which is -5i plus 5j. Remember that this is multiplied with the negative value here, and positive 10k. Now we will cover the definition of moment. Moment is a vector quantity and is defined as the cross product of a radius vector emerging from a given point with a force vector. The right-hand rule is a quick method of finding the moment axis of a simple 90-degree system, where the magnitude of the cross product is just the product of the force and radius magnitudes. To find moment about a specified axis, we first find the general moment axis using the given force and radius vectors, then perform dot product multiplication with this maximum moment vector and desired moment axis. This method allows us, in its most simple form of the unit vector being I, j, and k, to separate the moment vector into its moment components about the coordinate axis. So if I were to rewrite this equation in determinant form, I would have to use lambda x plus, or not plus, lambda y, lambda z in the first row. The second row would be rx, ry, rz, and the third row would be fx, fy, and fz in determinate form. Now let's do a moment calculation problem. Please pause the video and take 5 minutes to attempt this problem yourself. Now that you have attempted this problem yourself, we'll go over our approach. So first we are asked to find the moment from the cable at D about the point A. The tension from the string at D and the radius from A intersect at point E, here. We reduce cable ED into a unit vector direction, as seen here, and multiply it with the tension magnitude to find force ED, pulling away from the radius EA. The radius vector is simply 2.3 meters pointed straight upwards, so 2.3j. Now we form our determinant with the radius vector in the middle row and the force vector in the bottom row. We solve this determinant and get our answer as shown here. So next we are asked to find the moment from the cable at C about the moment at A, about the point A. There is no direct physical connection of radius between the force vector, which is the same direction as CG, and the radius vector, which is technically AG. However, we are able to create the radius vector by noting the length of AB and BG are the components of the non-connected radius vector. So AB and BG. We reduce cable GC into a unit vector direction and multiply it with the tension magnitude to find force GC, pulling away from the radius GA. Now we form our determinant with the radius vector in the middle row and the force vector in the bottom row. We solve this determinant and get our answer as shown here. It's just a little bit harder than the first part of the problem. This marks the end of tutorial 2 of MECH 2020 Statics and Dynamics. The topic of the next tutorial will be examples and practice problems on moment, as well as the principle of transmissibility and its application in moment. If you have any additional questions on the content featured here, You may email your course professor or tutorial instructor. Until then, goodbye.